Good morning, everybody. Sorry for the delay. I was having a little bit of network trouble. Give me just a moment and we'll get started. All right, let me go ahead and share my screen. Could somebody let me know if you're seeing the screen okay?
Yes, ma'am.
Thank you. All right. So just to let everybody know, I did score the midterm exams over the weekend, and you can check your scores in the Canvas gradebook. If you have questions about your exam, I would ask that you reach out to me and let's set a time when we can individually discuss it, right? I don't like to discuss people's exam in the open classroom, okay? So, just reach out to me and I'm more than happy to go over your exam with you. All right, so here we are in week 9. Let me remind you that your project article has to be approved by this Saturday at 11:59 p.m. or you lose points on your project. You see here on the screen, you lose 20 points if you don't get your article approved. And we'll start talking next week about what happens if you didn't get an article approved beyond losing 20 points, okay? To get your project article approved, you have to email me the full article as a PDF attachment. And once you send it to me, I'll take a look and tell you if it's acceptable. If it is, then you can go ahead and begin reading and preparing to do your summary. If it is not acceptable, I will explain to you why, so that you can begin to look for, something different, right? So just to remind you, the information on the project is available a couple of ways. I just got to it through the weekly overviews. You can also click on the assignments and activities tab and get to it that way, okay? And in the project details, I cover for you the specifics on the article that you're supposed to be summarizing, okay? So it's supposed to be a peer-reviewed research article. The goal is for you to read that article and tell me about it in your own words and tell me how it connects to this lecture class, right? Remember, if you are in lecture and lab, you have to do 2 different projects, meaning you need to have 2 different articles approved, and your articles must be related to one of these 5 categories. Remember, I am looking for physical science articles, not economics articles, not history articles, physical science articles, not chemistry. So be mindful of that. The article has to be science oriented, and in particular, physical science oriented, okay? So you can find these articles by using a college database, electronic databases, again, at whatever library you choose. Since you're a NUNES student, I suspect they have some type of library array available to you. You would have to find out from the library how to use the electronic databases. I'm sure they'll be happy to explain that to you, but that's not something that I cover because it varies from library to library. You can also use the website that I've bookmarked there, Hindawi. You can see the URL information here. If you click there, you can do a search for, whatever article topic you're interested in, as long as it falls within these guidelines. And, once you find the article, you can save it, download it, and then send it to me to review. For those of you who might be wanting to use a mobile app, or if you're using your phone or tablet to find an article, is our Exif mobile app is freely available in the Play Store, iTunes Store. That's what the picture looks like for the logo, so that you know what you're looking for. Now, just to remind you, the article that you're looking for, not the summary that you have to write, okay? The article has to be 15 pages long, but you cannot include the references in the page count, okay? So 15 pages long, the article body itself, not the references, okay? And you need to send me that article by email to review it prior to the deadline, 11:59 p.m. on this Saturday, okay? So do you have any questions for me on that? I covered this once before, but I wanted to just give a quick synopsis again so that you know what you're looking for if in the event you are looking. Also, in the announcements, I put some videos. You have to scroll through and find the ones that deal with the project, but there are, project videos. There are videos that discuss the project. So feel free to take a look at those, as you need to help. And then of course, you can always reach out to me for questions, all right? Any questions on that? Oh, I apologize, I didn't start my video. Sorry about that. All right, so since I don't have any questions on the project article approval, let's go ahead and get into this week's material. So this week we're continuing to look at laws that have been credited to Isaac Newton. We looked at last week his laws of motion. And so this week we're going to look at another law by Newton, and that is the universal law of gravitation. Okay. And so some things that we're going to key in on are listed in the objectives, and that is the inverse square law. Of course, we're going to be looking at how the gravity force affects objects. We'll look at the connection between the gravitation formula and the circular motion formulas that you already learned. So we'll be seeking to describe circular motion in a different way based on the gravitational force. And I will apply that particularly to orbit motion because that's an example that we've looked at so far. Of course, we'll be looking at the formula for the universal law of gravitation and get comfortable with the variables in the formula and how they relate to each other. And then we'll look at solving some problems with the universal law of gravitation. So today, my goal is to introduce you to the law. And then on Thursday, we'll solve some sample problems with using the law of gravitation. And also, we'll look at the relationship between our circular motion formulas and this new gravitation formula, okay? So that's where we're going this week. Of course, you have some items on your plate. Gravitation discussion is due this Saturday. And also problem set 6 and 7, because remember, I split things up for you, right? So that you would have a little bit more time last week regarding the midterm. So this week you do have to do problem set 6 and 7. And both of them pertain to Newton's laws, right? Because remember, problem sets lag a week behind. So both of those, are on last week's topic, okay? I do have available for you some notes from the CK12 textbook in chapter 6. And if you notice that chapter 6 kind of, you've used that once before, when we looked at circular motion. So that's why I put it there again. There are also some nice videos on gravitation that I made available to you. And then my supplemental notes, okay? So these notes are designed to introduce you to gravitation and the formula. Then on Thursday, we'll use the formula to solve some sample problems and then look at how this new gravitation information connects to our old circular motion information, okay? All right. Just a reminder for those of you that might, be having some challenges in the course. I just want to remind you of, how you can put your best foot forward in this class if that is not the case already. I'll keep harping on the importance of engaging with the material and engaging with me when you have questions, okay? So again, these objectives are what we're focusing on, okay? And so here we go, right up front. So what does Newton's universal law of gravitation say? Every particle, I like the word object, right? But particle is just as fine. I don't want you to be, I just like the word object because it gives a different connotation, but the word particle is fine. So every particle in the universe attracts every other particle in the universe with a force along a line joining them. So if we take any two objects, any two particles, and we draw a line between them, okay, each one is pulling on the other along that line with a force that's equivalent to, you see the formula given, right? I'll explain those parts in just a moment. But I want you to try to wrap your head around what they're saying, okay? So remember, we define gravity as this force of attraction between objects, right? And so this attractive force means each particle or each object is pulling on the other, right? And what this says is that they're pulling on each other with the same amount of force, okay? And this force of attraction between them is what we call gravity. And this can happen between any two objects in the universe. Pick any two objects in the universe, okay? They're pulling on each other. So right now, you are literally pulling on every single object in the universe, and every single object in the universe is pulling on you. Now that's a pretty incredible and powerful statement, given that, we don't have the capability of going everywhere in the universe, right? I mean, we haven't even been able to really travel anywhere in our solar system except for the moon in terms of human beings, right? And for Newton to make that statement long before we ever were able to do that is pretty incredible, right? I mean, Newton theorizes this through a series of mathematical exercises that he went through. He comes up with this idea of what is gravity, right? I mean, you might have heard the story. He's sitting under the apple tree, the apple falls, hits him in the head, knocks him out. When he wakes up, he says, voila, gravity, right? Well, that's not quite how it happened. He had to go through a lot of mathematics to get that done. But out of that mathematics comes one of the most profound statements about how our universe behaves. And that is that this fundamental force, gravity, exists between every object in the universe. Now, the question then becomes, how much is this gravity force? If you pick two objects in the universe, how much is the force between them? And so Newton is able to come up with this relationship. And you see it listed in the box. F, which stands for the force, in particular the gravity force, right, is equal to big G times M, little m, times big M divided by R squared, okay? So these two M's, the little m and the big M, are the masses of our two objects. And R is the distance between them from center to center, okay? We don't have to really worry about that too much, the distance between them, okay? And then this other value in the formula, big G, is what we call the gravitation constant. Some books will call it the universal gravitation constant. So with this formula, we can figure out the force of attraction between any two objects in the universe if we know their masses and how far apart they are, okay? So that's a pretty powerful formula, all right? Now, let's dig a little bit deeper into this big G. We'll see in just a few. I don't know if let me see if they don't give the value of it here, but let me open up a whiteboard and I'll show you. Okay, are you seeing that okay? Somebody let me know, are you seeing the whiteboard screen?
Yes, ma'am.
Thank you, okay. So I'm gonna write out the formula again, all right? And I like to do this right here. I like to put the big G down there because it reminds me that I'm looking at the gravitation force. So big G, little m, they do big M, little m and big M, that's fine. Some books will do M1 and M2. And here's the distance between them squared. And remember, if you're finding force, the unit is newtons, okay? All right, so now we know these are the masses, this is the distance between them. Notice that the distance between them is in the denominator and it's squared. So this F of G, you can look at it this way, is proportional to, make a better G than that. Ooh, let me undo all of that. That's ugly. This F of G is proportional to 1 over R squared. Okay. So this is what we call the inverse square law, because inverse means 1 over, and then you notice that that distance is being squared. Inverse . Oh, no, I gotta spell square right, huh? I need more coffee this morning. Okay, so we can see from this relationship that the force of attraction between objects obeys an inverse square law, meaning it's proportional to 1 over the distance squared. So for example, if I increase the distance, let's say I make the objects twice as far apart, well, the force doesn't get 2 times smaller. Because this is being squared, it gets 1 over 2 squared, which is 4 times smaller. Let's say, for example, I make the objects 3 times further apart. So the force doesn't get 3 times weaker. it gets 1/3 squared, 9 times weaker. Okay, so that 1 over the distance squared, that inverse square law. Don't forget, whatever the factor is, you have to square it. So let's say, for example, I cut the distance in half. Okay, so this, let's say R, I'm gonna show you how this works. Ooh. So let's say this. So R is cut. Because I don't want you to mix it. R is cut in half. Somebody unmute and tell me when I say R, the distance between the objects is cut in half. What does that mean to you? Anybody? So it means what? They're closer, right? And in fact, if R is cut in half, that means they're 2 times closer, right? But now, pay attention to this inverse square law. So if R is cut in half, you take 1 over 1 half squared. Okay, 1 half squared. And that becomes 1 over 1/4. Because 1 half squared is 1/4. This means then that the what? The force is 4 times stronger. Okay? We cut the distance in half, which means they're 2 times closer. But the force is 4 times stronger because of the inverse square law. Okay? So it's not a 1-for-1 thing. Okay? So that's, an important feature of this gravitation law. All right? Another important idea of this inverse square law is this big G. So I'm going to open up another whiteboard, and don't worry, I'll make all these whiteboards available to you. Okay? So another important feature of this formula, let me just rewrite it again. Big G, little m, they like to use little m and big M. Remember, some books might use M1 and M2, okay, over R squared. And remember, if you're finding force, the unit is newtons. I want you to get in the habit of that. Some of you lost points on the midterm because you didn't put units when you were supposed to, or you put the wrong units, okay? It's very important that you get the units correct because remember, this is about measurement. And if your unit is wrong, your measurement is wrong, okay? So now let's look at this big G. This is the gravitation constant. Some books will call it the universal gravitation constant. Sorry about that. Gravitation, okay? Ooh, that's ugly. Okay, took me forever to write that. Okay, gravitation constant. All right. Now the question is, what is the value of it? Okay, so 6.67, some books will write 6.673 times, and let me fix this 6 right here. 10 to the negative 11. And here we have to have units now, because that's Newton times meter squared per kilogram squared. Okay, so that's the units for the gravitation constant. Okay. Now, one of the things that should immediately jump out at you is how small this value is. 6.673 times 10 to the negative 11. That's an extremely small value, which means for objects to feel the force of gravity, they have to be fairly large in size, okay? So let's say, for example, right now you're sitting in front of your computer screen, all right? So because G, this big G, this gravitation constant is so small, you don't have to worry about the force of attraction between you and your computer screen being so large that the computer sticks to your face. Okay, there's no chance of that happening because your mass and the computer's mass, even though they're being multiplied together, cannot overcome this very small gravitation constant. Now, if you start putting in objects like planets, okay, that have a very large mass, then you can overcome this small gravitation constant and produce a force that can be felt. Like if we put in your mass and the mass of the Earth in there, your mass might not be that big, but the mass of the Earth is huge. And so it'll be able to, you know, cancel out some of that 10 to the negative 11. Okay. So we have to have objects that are fairly large in size. The other thing is that this distance, because it's a 1 over r squared or an inverse square law, if objects are far apart, then the amount of gravitational force will be, you know, small, right? And you're already dealing with a small value of big G. So that's going to make it even harder. So think, for example, you and Jupiter. Jupiter is so much bigger than the Earth, right? So you're like, okay, I got my mass and I got the mass of Jupiter. And that's very big, way bigger than the Earth. So I should be able to feel that force, right? But think about how far Jupiter is from here. Okay. So even though it's so much bigger than the Earth, because it's so far away, and because that gravitation constant is so small, you don't feel any of the effects of Jupiter pulling on you. In fact, your weight, the amount of gravity, you know, the pulling on you, right, is primarily due to the Earth because it's the largest and biggest thing close to you. So you have to have very large objects and they have to be relatively close for that force to be appreciable or noticeable, okay? So, you know, you have to keep that in mind when you're using this formula. And on Thursday, what we'll do is we'll look at using this formula to solve some sample problems. And then we'll tie this force into a force we've already looked at, and that is for circular motion, okay? So I'll make those whiteboards available to you so you can have that information handy. So as I was saying, you have to have some objects that are fairly large in size for that force to be noticeable. And that is why, we experience ocean tides on planet Earth. That is because our closest neighbor, the moon, is fairly large in size. The Earth is large in size. And so the moon can exert a force on the, on the water that's found on planet Earth, okay? And so that water can be distorted, because of that gravitational pull between the Earth and the moon. And that's what results in low tide and high tide, okay? So that's an example of where gravitation, that gravitation force is noticeable. This idea of weightlessness and microgravity is another area where this whole gravitation and gravity business is relevant, right? One of the things that I love to investigate is this idea of orbit motion. And you see these astronauts that are out in the International Space Station. They're just moving about so freely, and they feel this phenomenon called weightlessness. They're not actually weightless. It just feels that way because they're in a craft, the space station, that is free falling around the Earth, okay? So the craft is free falling. They're inside a craft that's free falling, so they're free falling, and that creates that weightlessness sensation, okay? Sometimes you might see this whole idea of weightlessness, when they talk about being in an elevator and the cable gets cut and the elevator starts to free fall, right? So if you're inside that elevator, when it starts to free fall, you will be free falling. And so you will feel that sensation of weightlessness. You will not actually be weightless. You just feel that way, okay? Another, phenomenon or term that you hear thrown around a lot is this idea of microgravity. Okay, let's be clear. There's gravity between every object, any two objects in the universe, right? But this idea of this small net acceleration that astronauts and other objects in orbit experience, not because of gravity, but because of their motion, we call that as microgravity, okay? And so we'll look briefly at Kepler's work here, and that's what we're leading up to here now. We're not gonna jump deep into Kepler's work, but I'm going to it for a purpose, so just bear with me on that, okay? So, human beings have been curious about the planets since we've been human beings, right? We wanted to know about these objects that we saw in the night sky, okay? So the ancient observers, they didn't have all of the tools and technology that we have, but they were able to do some observing, right? Either with the naked eye or with some rudimentary telescopes, right? And so the Greeks, for example, call the planets that they saw in the sky wandering stars. They didn't know the difference, or they didn't distinguish between them, okay? And so, the only thing they knew was that some things in the sky were stationary, pretty much stayed, maintained their position, and some things wandered around. And so they labeled the planets wandering stars. And then you have this astronomer Ptolemy that began trying to explain what he saw happening. Now, I will say this: long before the Greeks, there was other civilizations that had, strong knowledge of the stars and planets, right? But we rely a lot on the work that the Greeks did because, it was documented, and that information was available to us. But also because it did provide some of the strong foundation that we built on, right? That other scientists built on, all right? And so the Greeks, in trying to explain the motion, came up with this concept of epicycles, okay? But here's the thing, they put the Earth in the middle and supposed that the Earth was stationary, okay? Well, we know that definitely is not the case, but think about it as a starting point of trying to explain the motion of the planets. Now, why is that important? Because it's this understanding of the motion of the planets that ultimately leads Newton to formulate the law of gravitation, okay? So while the Greeks didn't get it right, and then even they were some other scientists that didn't necessarily get it right, when we get to scientists like Tycho Brahe and Kepler, Copernicus, Galileo, they all had that role in helping us to understand the motions of the planets. But probably one of the most important scientists in moving our understanding forward was Kepler. And that is because he abandoned that idea that the Earth was the center and the sun and everything else revolved around it, to this heliocentric view that said that the sun was actually at the center and the planets revolved around the sun, okay? And so Kepler did quite a bit of observing and data collecting, and he took all of that information and formulated it into 3 laws of planetary motion, okay? So see, he went beyond with his work and really trying to come up with a more formalized way to explain the motion in these 3 laws. Now, I don't want we aren't going to use these laws. We'll focus a little bit on the 3rd law, and you'll see why. But his first law looks at the orbit of the planets, and as I mentioned to you before, we can use a circular orbit for most things, and but truthfully, the orbit of the planets is elliptical, right? But we're not going to get into using that in any way. Just to know that we can model the motion of the Earth around the sun, for example, using a circular orbit, but that's not truly how the orbit is shaped. But, as I always like to say, good enough for government work, right? His second law, okay, looks at this idea of the area that the planets sweep out as they revolve around the sun, okay? So if you look at a planet that's orbiting and you pick out different spots along that orbit, but you measure the distance traveled, the area swept out within equal time periods, that's going to be the same. So what he's saying is, if you look at the picture, the area 1, area 2, and area 3 are the same because the time that it takes the planet to go from A to B or C to D or E to F is the same, okay? So sweeps out equal areas in equal times, okay? And that's a pretty important concept, and that was one thing that he was able to figure out through his observation and measurements. okay? And then Kepler's third law, okay? So what we're looking at here is the relationship between the periods and the radii, okay? So if we take the period of any two planets squared and put them in a ratio, that is equal to the ratio of their radii cubed, okay? That's a pretty powerful relationship to figure out. It tells you something about the extent of the work that Kepler was doing. Why is Kepler's work so important? Well, as I mentioned, Newton comes along and he utilizes Kepler's laws to help him uncover the universal law of gravitation. And it's here that he starts with this idea of the relationship between the periods and the radii. You see, Kepler was brilliant and he was able to measure and come up with these three laws. But the one thing he could not do was explain why the planets orbited. He could measure everything about them. He had tons and tons of data, lots of observations going on, but he couldn't answer the fundamental question: what's keeping them in orbit? Well, see, Newton comes along and takes Kepler's work and answers that question. And he doesn't just answer it from the perspective of, sitting under the apple tree, the apple falls, knocks him out, and he wakes up and says gravity. No, he has to go through quite a bit of mathematical exercises, theoretical exercises, as we would say, to uncover the relationship between the gravitation force between two objects, okay? So he had to do quite a bit of work to be able to see the pattern that the masses had to be multiplied for the two objects, and you had to know the distance between them, and that had to be squared and put in the denominator. Now, truthfully, when we look at Newton's law of gravitation, let me bring up one of my screens here. When we look at this law of gravitation, this is not the ultimate form that Newton came up with. This is a combination of work done by Newton and a fellow named Henry Cavendish. Newton came up with the inverse square relationship, and the idea that the force of gravity was proportional to the masses. So we could also, we could see here from the work that Newton did that is proportional to M1, big M times little m. So he figured out that this force of gravity, and let me write this as proportional to. He could see that this force of gravity was proportional to the product of the masses and the inverse relationship of the distance squared. This is Newton's work right here, okay? Which is pretty powerful, but he didn't actually come up with this complete formula. The reason he couldn't do it was because when he was working back in the, 1600s, 1700s, we didn't know the mass of the Earth. So he couldn't completely write the formula that explained how gravity worked. But 100 years after Newton, a fellow by the name of Henry Cavendish comes along, and experimentally, he finds the value of big G. Now, I want you to think about that. 100 years after Newton, we finally know the mass of the Earth. So he comes along and he uses that value to figure out big G experimentally. And once he finds big G experimentally, we realize then that Newton was absolutely correct. And that's why Newton is given credit for the law of gravitation. But it's not something he figured out totally by himself. He had help from Cavendish 100 years later. Now think about it. Look how small that value is, times 10 to the negative 11. We would be challenged to go into a laboratory and measure something that small today. And yet, well over 100 years ago, he was able to figure that out experimentally. So that's quite an incredible feat. That's quite an incredible feat for Newton to propose this relationship and for Cavendish to experimentally verify. And then 100 years after Henry Cavendish, Einstein comes along and he gives us a different view of gravity, but it is consistent with what Newton and Cavendish proposed. Okay. So that's kind of like a window into how science proceeds. Everybody comes along and adds their 2 cents to it. But it all got started because of Newton and his curiosity to explain why the planets orbited and why objects fell to the earth. Okay. And he even borrowed from other scientists like Kepler and Galileo. Okay. So on Thursday, we're going to take this equation and we're going to actually use it. And then we'll look at how does this force, this gravity force, connect to the uniform circular motion that we looked at several weeks back when we looked at the satellites, for example. Okay. So I'm going to stop my share and ask if there are any questions. I see Nikki and Hosea still here. So Nikki and Hosea, here's what I need for you to do for me. I need you to email me and say, hey, Doc Z, I was in class this morning and I stayed until you finished covering the material. If you do that, I will award you 5 bonus points and you can tell me what you want to do with those bonus points when you email me. Okay?
Thank you.
I knew I'd get a response on that.
Thank you.
Yes. Okay. So you have to email me. If you don't email me and say, hey, I was in class this morning and I like to use my 5 bonus points for, if you don't tell me, then I won't know what to do with them. Okay. All right. So that concludes what I have to present. If you have any questions, feel free to unmute, ask your question.
Have a good day.
You do the same. I'm going to stop recording